Now Chebysheff's theorem just says that in any distribution, at least, so this is a lower bound or a minimum, 1 minus 1 over k squared of the values, that proportion, that fraction of values, absolutely must lie within k standard deviations of the mean. So in this case, if k is 1, what would that look like? Well, if I plug 1 in for k, then I get 1 squared, and then 1 over 1 is 1, and 1 minus 1 is 0. So what Chebysheff's theorem says is really none of the data values have to lie within 1 standard deviation of the mean. Well, that's not very useful at that point. Okay, so we really start with k equal to 2. So if I take 2 and plug in for k, and I square it, I get the 4, and 1 minus a fourth is 3/4, which is about 75% of the values, right? So in this case, at least 75% of the data absolutely must lie between the mean minus 2 standard deviations and the mean plus 2 standard deviations. Notice in this case, 75% is 20 points lower than the 95% we used with the 68, 95, 99.7 rule. But you're guaranteed to have at least 75% of values within 2 standard deviations of the mean, whereas the other rule is sort of what works empirically, or it's been observed to work pretty well in most cases, but not necessarily all. Now if we go on down to k equal to 3, then what we get is, well, 1 minus 1 over 3 squared gives us a fraction of 8/9, and then if we round that off, that's about 88.9%. So Chebysheff's theorem says that at least 88.9% of the data has to lie between mu minus 3 sigma and mu plus 3 sigma. So let's look at an example. Suppose that the weights of new cars have a distribution which you're told is positively skewed, or skewed to the right. Now the mean is 3,480 pounds and the standard deviation is 205 pounds. So let's start by estimating the portion of new cars which weigh between two amounts, 2,865 pounds and 4,095 pounds. Secondly, we'll come back and estimate, okay, how much do we think at least 75% of new cars weigh? So it's two different ways to apply Chebysheff's theorem. So let's begin with part A. Well, where does 2,865 pounds come into play? Well, if you look, 3,480 minus 3 times 205 will give you that lower bound of 2,865. Similarly, if you add 3 standard deviations to the mean, 3,480 plus 3 times 205 will give you 4,095. So these numbers are actually the values for mu minus 3 sigma and mu plus 3 sigma. Okay, in that case, we have k equal to 3, so we're in this last section, okay, talking about Chebysheff's theorem that we've displayed. So what we can say is what? Well, from Chebysheff's theorem, I would say at least 88.9% of all new cars, and that comes from right here, weigh between 2,865 pounds and 4,095 pounds. Okay. Now, what about part B? Well, with part B, we're saying, okay, if I want 75% to be the minimum amount I've captured, okay, so we're up here at the 75% value, then I want to go k equal to 2 standard deviations on each side of the mean. So if I do that, what do I get? We'll start with the mean. So let me scroll back up just a little. 3,480, subtract 2 times 205. So when you do that subtraction, you get 3,070. Then go back and add 3,480 plus 2 times 205, and you come up with 3,890. So then what I can do is say that according to Chebyshev's theorem, at least 75% of all new cars weigh between 3,070 pounds and 3,890 pounds.